Right, so welcome to this video where we're going to be having a look at something called Pascal's triangle, which a number of you might have kind of been aware of before. It was invented by a French mathematician. There he is, Blaise Pascal, in the 17th century. Now, Pascal he wasn't just a mathematician, he was a philosopher, he was a physicist, he was a theologian, most famous firstly for the triangle we're going to be having a look at, and also something called Pascal's wager, which was his way of being able to use logic to determine whether or not one should believe in a god. Like say, he was a theologian as well as being a mathematician, and just all round kind of big thinker and egghead. But we're going to have a look at his triangle today. Now, you might be looking at this because you're starting to have a look at something called a binomial expansion in your algebra, or it might be that you're starting to look at probability and you're going to be looking at the binomial distribution. Either way, both of these things make use of the values that appear in Pascal's triangle. So we're going to have a little look at where the triangle comes from and what those values are. So by the end of this video, you should know what the binomial coefficients are and that they come from the triangle. You'd be expected to recognize the first few rows from the triangle, but as the triangle gets bigger, the numbers get much higher, and so we have to know how to use a calculator to be able to calculate them, and that's something we'll be having a look at towards the end of the video. Now, we'll start off. Anytime you've been to kind of the seaside or kind of a fair, you might have seen a game where you have to drop coins into slots at the top and it bounces through a series of pegs and the coins drop into the bottom, and then any that fall back into the tray, kind of into the sliding trays, you get to win. Well, that's what we're going to have a look at. A system where we've got balls dropping through a series of pegs. So let's have a little look at how this is going to work. Now, what we've got here is a simulation I've been running for quite a while now. So you can see the balls dropping into the system of pegs at the top, and where they drop is just counting kind of where each ball lands. And you can see straight away that most of the balls are dropping into the middle. And you've got a symmetry of how these balls are falling. What that means is it appears to be far more likely that these balls are dropping into the middle of the grid rather than to the outsides. And so what we're going to do is have a little look at kind of why that happens, and then link that whole thing back to Pascal's triangle. So let's just jump back to the slideshow. Here we go. And the key to it, and the reason why there was more balls dropping into the middle, was to do with how many routes there are through the image to get to each of those coloured squares at the bottom here. So we've got those coloured squares, and we're going to have a little look at kind of how many times the balls can drop through. So I'm just going to drop into another program now, just so we can start having a little look at how that's going to work. Okay. So if we imagine this first grid over here, we've got a triangle with just two rows. The ball comes into the top, hits the first peg. It's got an equal chance of going either left or right. So let's say it's going to go left, drops down, hits the next peg, can go left or right, and ends up in that tray at the bottom there. Now, clearly, from looking at it, we can see there's only one possible route that a ball can end up in that tray there. So I'm going to put a 1 in there to indicate that one route. Alternatively, the ball might come down, hit the first peg, go this way, but this time, instead of going left, it goes right, and that would make it drop into the middle tray. But you can see as well, though, if the ball comes down, hits the first peg, but this time goes right, hits the second peg, goes left. So you can see clearly what we've actually got is two routes through this system of grids to get into that middle tray. And then to get into the one in the end, again, it's got to go down, it's going to go right again, into the tray there. And so there's only one possible way that can happen. So we've got a series of numbers that have got one route, then two routes, then one. If we consider the next triangle over here, where we've now got three rows, and effectively the numbers that I've got in my grids here effectively are the ways of reaching each of these third balls here. So we know there's only one route of getting to that ball there, we know there's two routes of getting to that one, and we know there's one route of getting to that one. And again, if we consider, okay, how can we get into this far left-hand tray? There's one route to get to there, the ball must go left. There it goes, into there. There's only one way that can happen. There's one route. Similarly, the ball might go right at this point, so it can get in there. So that could be a route to get into that second tray. Or it could come from this one. And we know there's two ways of getting to there, so in total what we've got now is 2 routes coming from there, 1 from there, so there's got to be 3 routes to get us into that tray. Similarly for the next one along, 2 routes coming from this peg, and it hits that bottom tray there, and so we've got 2 routes coming from there and 1 coming from that side. So we've got 3, and then finally the last one, clearly there's just going to be 1 way it can get in there just by going right every single time. And what I'm going to do is just look at kind of the next row down. We won't go any further than this, but we can see here now what we've got is 1 way of getting to there, 3 ways of getting to that peg, 3 ways of getting to that peg, and 1 to get to there. So that would leave us, again, 1 route to get to there. If I'm going to get into this tray, it can come from there, or it can come from there. So I've got 3 plus 1, so 4 ways of getting in there. Now, if I'm going to hit this middle tray, we could come from 3 routes from there, or the 3 routes coming from there. Well, my arrows aren't the greatest, but never mind. And so that gives us a total of 6 routes there, and clearly due to the symmetry, 4 there and 4 there. So what we've got is from the first one, 1 2 1, then 1 3 3 1, 1 4 6 4 1. And you'll notice that if you consider this 4 has come from adding together the 1 and the 3. The 6 has come from adding together the 3 and the 3. And this is how Pascal's triangle is going to start being built. So what we just saw from previously was we've got these values 1 2 2 1, 1 3 3 1, 1 4 6 4 1. Now Pascal's triangle essentially is built up in exactly the same way. So we're starting at the top here with a 1. All the outsides are going to be 1. So we're now onto this row here. This is the row where we're going to get 1 2 1. The next row down, 1 3 3 1. And again, the 3 here is made from adding together the 1 and the 2. This 3 is made from adding together the 2 and the 1. The next row, that's the one we saw from the previous slide, 1 4 6 4 1. So this is technically what we're saying here is this one at the top is row 0, then we've got row 1, row 2, row 3, row 4. And then this next one here is going to be row 5. And again, we're going to get those values from adding together the 2 numbers above it. So on the outside, we've got 1, then 5s, 10, 10, 5, 1. Again, clearly you can see the 10s here coming from the 6 and the 4. And Pascal's triangle just keeps going like that. So the next row down, we get the numbers 1, 6, 15, 20, 15, 6, 1. And finally, the bottom row, there we go. And we could just keep building and building and building, getting ever bigger numbers. Now, Pascal's triangle, there's all kinds of associations going on in here. You'll notice that you've got the counting numbers, 1, 2, 3, 4, 5, 6, 7, there they are. You've got the next ones here, 1, 3, 6, 10, 15. Those are the triangular numbers. You'll notice 1 and 3 makes 4, 3 and 6 makes 9, 6 and 10 makes 16, so you can make the square numbers. And there's all manner of different associations between the numbers going on in Pascal's triangle. If you wanted to study that further, there's plenty of websites that can help you look at all the different associations in there. As far as we're concerned with our studies, what we're going to look at is the fact that we know each row is symmetrical. We know each value is created by adding up the 2 numbers above it. And as it turns out, we don't need to draw out the entire triangle to be able to calculate these values. They actually come from a formula which looks like that. So we've got the notation here, which is NCR, and it says N, now the exclamation mark means factorial, which means if I take n numbers and times them all together, so that's n times n minus 1 times n minus 2, and so on and so on and so on and down. So for example, 4 factorial would be 4 times 3 times 2 times 1, which is 24. Again, you will study factorials further on as you get later in the course. We'll put the formula there so you know there is a formula that calculates it, but you'll notice on your calculators you'll be able to find an NCR button, which is on top of the divide symbol on your calculators. And that button will help you calculate the values from Pascal's triangle. So for example, if you have a look at the bottom row, that value there is 7C0. Next one is 7C1, 7C2, and so on and so forth.